Hi everyone, this is Dr. Babak Parkhideh. I'm a professor at University of North Carolina at Charlotte and CEO at Teleye Technologies. Today I would like to talk about the need for speed, high speed in space power electronics in particular. Would like to walk through some of the needs to enable those technologies. So I briefly talked about fundamentals, current developments, and then some of the case studies that we have done in the past 2 years. So the first one is power electronics. So whenever there is a mismatch between the source of power and load, we need some interfaces. Most often, these interfaces are electronic and electronically controlled. The source being like a solar PV array, and the load can be anything like a laptop. So one type of these interfaces are so-called switched mode power supplies. And they're equivalent to DC voltage equivalent, transformer equivalent, like changing the voltage from certain level, let's say 120 volts to 12 volts, for instance. The reason that we basically adopt this technology for many applications, including space applications, ideally there is no lossy elements. And therefore, the efficiency of these converters are theoretically can reach to 100%, which is ideal. You don't need to really worry about big basically heat dissipation mediums. Of course, in reality, all these components are lossy. But to enable these technologies, we need passive elements such as inductors and capacitors that are shown here. So basically, the size of these inductors and capacitors decreases with the faster switching that we have in these converters. So these are just two examples that I provided that's showing like at low power range, if we need certain amount of henries for the inductors, basically we are able to operate these converters at, let's say, 100 kilohertz. If we increase the switching frequency, fundamentally what it happens is that the amount of inductance needed for these converters are reduced, and therefore the size of these elements are reduced significantly. So this principle also applies for high power application, where you can see a typical service transformer at 250 kVA that we use at 60 hertz. And if we are able to increase it to, let's say, 20 kilohertz, we can reduce the size, whether it's dry or liquid cooled, significantly. So the enabling technologies that allows us to increase the switching frequency are basically wide bandgap semiconductor power devices that enable much more efficient semiconductor switches. And we are able now to increase the switching frequency with inserting no additional losses. So theoretically, when you look at these devices that are commercialized today, such as silicon carbide and gallium nitride, with respect to all the performance metrics are much better than silicon. For instance, increase the band gap allows us to operate them at higher temperatures, or increase the electric breakdown field, enable us to make them much smaller while we can increase the voltage significantly. So what are the applications? So obviously all these interfaces are now seen in many applications, including space. So the silicon still remains the mainstream technologies, but now these devices, now we're exploring many more applications. Right now, silicon carbide based power electronics are now used at extended power, right? Like at maybe hundreds of kilowatts, and the frequency tens of kilohertz, whereas GaN are basically used for multi-kilowatt range, mostly even below kilowatt range, but at elevated frequencies, and therefore we can reduce the size of these converters extensively, as I just explained. The applications today basically are diverse, and we think that these application domain, because of all this shift through electrification, will increase as well. So what are the components and maybe subcomponents that we have in any power electronics? As I explained, we had some power transistors, we had filters, we had controllers, and we have sensors. So right now, basically, there are several development of basically power transistor that I just explained using wide bandgap semiconductors, such as GaN, and now we have commercially available, almost like cuts, rad-hard devices available in the market. Filters also to shape the waveforms are also available. We are now exploring several embedded basically filters or a novel way of stacking different capacitor that are efficient at high frequency but need a high amount of capacitance. Microcontrollers and FPGAs are now accepting much higher frequency signals that enable us to generate much higher frequency switching signals. But we believe that there is a gap in sensing different parameters for control, protection, and prognostic of these power controllers. So one of the, I would like to walk you through some of the examples that we experience. Here is an example of a very high frequency power converter. And the intention of this converter was to have a solar power inverter basically on a single IC. And to enable to do that, basically we had to increase the switching frequency, and for controlling, we had to use off-the-shelf current sensors. What we observed due to the insertion of these sensors, we had to overcome, or we had to tolerate this much of overvoltage, and therefore we had to design the whole system based on these overshoots. And that moved us to a new class of voltage levels that no foundry could actually support. By removing those sensors and optimizing the layout, basically we could overcome the issue that we had here. We doubled the voltage and basically paved the way for this miniaturization. So today sensors are all invasive and prevent optimal use of power devices. The other, bottleneck today is sensors are just too slow. And here is another example of high-frequency power circuits that was substantially has very fast rise time due to reduced amount of inductance, as I just mentioned, to reduce the size and become mass efficient. But when you're using the off-the-shelf, state-of-the-art current sensors needed for these kind of applications, you see that you're missing most of the information available in the reference, and therefore it limits us to control or develop new types of converters. So these are some of the issues that I just wanted to show and share with you that we've seen in the past 5 years, and what we worked on to solve some of these issues. So the first case study was basically to develop now intelligent power stages. So far we had these power stages that, as I said, matching the source to the load with all dynamic performance that would require. But now when we wanted to add this intelligence, we wanted to see if we could perform this in a non-invasive and fast enough for these newer type of power semiconductor devices. In other words, can we do predictive maintenance? So as I said, there was no extensive history for these devices in harsh applications. these components have obviously, like others, have limited lifetime. And right now there are emerging applications, and now even space applications, we are thinking of the same thing. But now adding this predictive maintenance and intelligence require to have sensors and algorithms to do that. And what we are thinking, if there is any need for even have this decision, make it user defined and prolong maybe the lifetime of these devices, or even extend the range of operation when it's needed in critical applications. So toward that, we started looking at some of the reliability tests performed by NASA on even silicon devices used in power converters. So this is a very commercially available silicon power devices with more than 50 years of maybe experience. And you see that under harsh conditions, basically they behave differently. So now we started to look at it as the sample data, and we wanted to see if we can really predict the behavior, one of them, if there are enough sample, to train the devices with. So we studied this extensively, and this is one of the results I just want to show you, that by using deep learning, algorithms, now we can have very accurate, and I want to emphasize on accuracy, and now scalable solution that can be extended to other parts or components within a power system used in many applications, including space. So in this, what you're seeing is obviously in the beginning, with the prediction was not accurate, and we had maybe a high error. But as we learn more about this in real time, now our error to the predicted value is now very, very small. So we published this work in IEEE Transactional Internet of Things in 2019. But our problem, maybe of course on the algorithm side, and we extend that work, but now how can we make this available in the converter? Not like with lots of probes, but with a non-invasive sensors, part of the converter. So we were involved in different projects, like 1,000 volt DC, 75 kilowatt. And we started to understand this architecture. And this is a typical, converter that you can find in industry. It has different parts and filters. And now what we basically propose is to add, a board like stacked or sandwich between, different boards that's seen in a typical power converter. And by using the data collected by this, maybe we are able to measure those key signatures. And here is an experimental verification of that work. I remove other boards for more clarity, but basically this blue board is now a health monitoring device that now can basically measure the device behavior when it's exposed to 1,000 volts, and can measure really at millivolts level. And with this accuracy, can predict, it can measure or estimate, the on resistance or power device resistance during conductions. So by collecting this information and incorporated with our algorithm, now we have a tool that basically we can estimate maybe the remaining useful lifetime or other basically key decisions that makes this system more intelligent. Another case study and the need for high speed is coming from our NASA SBIR project that basically we dealt with, GaN converters, and we wanted to see if we can predict and even prevent catastrophic failure, and maybe basically increase the reliability or reduce the complexity power controllers. So this is basically a simple slide that shows that GaN devices are much faster than silicon. And because of this simple graph that you can see here, conventional protection methods are not basically applicable for GaN converters. Because we do not have non-invasive current sensors, we have to adopt voltage-based protection methods, which are temperature dependent and are just too slow. So therefore, in this project, we thought that if we could develop an ultra-fast, non-invasive current sensor that are non-invasive to the circuit, we can basically optimize the circuit and all, the system to basically add this feature. So in this case, what we did, we studied several converter architectures that we thought would be applicable for space applications. And we found how these circuits behave in terms of electric and magnetic fields, and basically we wanted to develop a sensor that can measure not directly but indirectly the fault current very fast. So here in this key basically example, what I want to show you is this is my line currents, like inductor current. As you can see, there is no transient seen. So if you place your sensor, obviously you do not even detect the catastrophic failure in the system. The blue is what it comes from the source, and even after fast capacitors. What it's shown here is basically they cannot really follow the switch current, which is the green line. And in this one, the purple line shows the subtraction. This current, we found that if we're able to access to this subtraction, we are able, and we designed a sensor for that in particular component. Now we have a chance to detect the short circuit without touching the switch and the layout of the circuit. This is the zoom in, of this again, showing that basically the subtraction of source current and the switch current is indeed the fault current, and we just had to look into which components contribute to this current. So we characterize this current, and that has been tested for many different systems, and we found that the frequency of which we need to detect in this system is about 30 megahertz. So to just give you an example, this is like the state of the art, and which is like a 1 megahertz 40 amp sensors, and this is like a ceramic capacitors that are used in many power converters, and that's a desirable choice for us to design our sensors in this size. So this is like one of the setups that we developed in phase 1 to show or demonstrate that how really the magnetic and electric field changes in different positions and points of these power converters, and develop different prototypes placed at different points to basically see if they're close to what we believe is a source of short circuit. And this is one of the results that basically shows that we found that in particular capacitor that found in many converters, essentially that signature is available, And now we are able to measure this with less than maybe 10 nanoseconds traced fault current, which is really fast. So in our design, basically, we considered all the issues around active circuits and complexities that we would see for space applications. And now we would like to also use this high frequency information to not only protect when the fault happens, but also if we can process this information, may reveal some more important information about predicting whether there is a change in dynamics of a system. With that, I would like to conclude my talk by basically saying that power electronics, as many knows, are critical to all space applications, like satellite and space stations, spacecraft. We are working on ground-based stations even for our NASA project. Rethinking power electronics, we believe, needs to happen sooner than later, mainly because of these newer generations of power transistors known as wide bandgap. Wide bandgap devices enable mass and volume efficient power supplies and controllers, but as I mentioned, we need fast sensors and efficient algorithm to optimize their utilization. And what I just mentioned, basically we can design smart monitoring, fault detection, fail-safe provision, without adding significant size or cost to existing, if not better. In general, with the new development that we see, we believe that basically we need to be proactive in our new designs for power converters and controllers and not just reactive. With that, I would like to thanks for your attention. I'm happy to answer any questions.
Okay. Oh, and everybody, if you have any questions here, you can type them in the chat and I'll read them out loud for Babak here. So yeah, we have one question already. It's, do you see the incorporation of silicon carbide semiconductors as high-powered devices that can be readily manufactured in situ for Mars colony applications?
So silicon carbide, in terms of rad-hard devices, I think they should follow same with silicon. So I think if I just want to address that, I would, I think, limit to that. But if we want to extend it to GaN devices, as far as I know, GaN devices are inherently much more tolerant because of the structure of a device compared to silicon and silicon carbide.
Okay, yeah. Oh, we have one more here. What is known of the long-term reliability of WBG devices? So
I mean, this is a great question. That's why we are thinking now we may add this intelligence, but obviously the reliability from the way that we look at it is different from WBG device manufacturers. They ran very similar reliability tests like what they do for silicon power devices, and they report many encouraging results. So right now, many electric vehicles use that. Lots of satellite power supplies are now using it. So basically, we really follow our experience in reliability analysis of semiconductor devices. So you should not get wrong. We do not develop unreliable devices. Otherwise, it doesn't make sense. but it's just doubt about the reliability. We just have to, I think, wait and see. But in the meantime, I think because we cannot create history, right? We cannot fast track that. So in my mind, now by adding these intelligences, as I just mentioned, I think we can just improve the reliability of that. I hope I answered your question.
Okay. Another question we have is, if you run these devices at low duty cycle, i.e. not as a power supply, does their reliability change significantly?
So basically, so during low duty cycles, in my mind, the only thing, I think for silicon carbide may not. For gallium nitride based devices, if you go more than 200 volts, there are some maybe transient changes in resistance that may or may not affect the reliability, but may affect maybe transient operation of other parts. So for instance, we develop platforms actually to evaluate the transient characteristics of GaN devices to measure now the dynamic RDS(on). So unlike what I just showed for silicon carbide devices, maybe just midpoints of the duty cycle is important. We only actually measure at high duty cycle. But for GaN, that's different depending on what technology, but the most promising technology, there's a change in transient behavior. Most of the manufacturers basically believe that does not cause any reliability concern as that signature drops over time. But I'm not the manufacturer of those devices, so that's why we developed that platform.
Okay. And then another question is, for GaN WBG devices, what about availability of GA outside of Earth sources? And could it be available on Mars?
So gallium availability, I do not know.
I would say let's go take a look.
Okay. Yeah.
But so far, it's basically on Earth, it's abundant. So it's not considered as rare earth material.